Hello again friends, and welcome to the channel Derive. In this video we'll derive the famous equation E equals mc squared, or more correctly E equals gamma mc squared. Alright, so how are we going to do this? Well, first let's consider that we have a spaceship. We have a spaceship and it's traveling close to the speed of light. Say it's traveling around 100,000 kilometers per second relative an observer on Earth. So an observer on Earth is seeing the spaceship and registering the velocity of 100,000 kilometers per second. Now imagine a photon traveling parallel to this spaceship, just outside the spaceship, with the speed of light. And the observer on Earth will register the speed of light, which is roughly around 300,000 kilometers per second. But what do you think that an observer on the spaceship will register as the speed of light here? Well, according to classical mechanics, he would register that the speed of light would be 200,000 kilometers per second, because the net change between 3 and 100,000, which is the speed by which the spaceship is traveling with, is 200,000 kilometers. Well, actually, what this observer registers is also 300,000 kilometers per second for the speed of light. So the speed of light, what we learn here is that the speed of light, c, is always constant, no matter from where it is observed. Always constant, no matter from where it is observed. And this is the first postulate of special relativity. The second postulate of special relativity is that the laws of physics are the same in every inertial reference frame. So what does inertial mean? Inertial means a reference frame that is not moving, or that is moving at a constant speed. And this means not accelerating. Not accelerating, and that's important. And if we think about it, if c is always constant, then some other factors must be adjusted in order for c to remain constant. And if we think about it, then this must mean that the sense of space and time is different for the different observers, because that's the only way by which c will remain constant. And how can we demonstrate this? Well, we can demonstrate this through a very simple experiment with a very simple clock model. It's called a photon clock. It's comprised of two mirrors that are being separated by the distance x. And there are two perfectly reflecting mirrors parallel to each other, and we have a beam of light between these mirrors. And the tick-tock of the clock is simply the reflection made of the photon. So this is a tick and this is tock. And as you can see, the time, we can write it as time naught for the photon to travel from this mirror to this mirror, will of course be x divided by the speed of light, which is c. Okay, so far so good. Now imagine an identical clock being placed inside a car that's traveling with the speed v, and this other clock being placed at the side of the road with an observer. And when the observer sees his own clock, he will of course see this. But when he looks at the car that is traveling with the velocity v, he will see something else. He will see that this beam of light is not moving up and down like this, but more in a zigzag motion like this, because the car is moving at the constant velocity v, and the clock is being perpendicular to the direction of motion. So this is what the observer at the side of the road will see when he looks at the clock, which is inside of the car. The speed of light is the same, c is the same, but the distance that is traveled for the speed of the light, according to this observer, will be greater than this distance, right? Which means that the tick of this clock will take longer than the tick of the clock that is just beside this observer at the side of the road. So we can write this tick or this time as t to tell it apart from t naught, from this time. The thing that is in common between these two scenarios is the distance between the mirrors. That remains the same, x, because remember the clock is placed perpendicular to the traveling motion. And if we think about it, we will actually have a right triangle here. This side will be x, the hypotenuse will be ct, and this side will be the velocity of the car times t. And by the Pythagoras theorem, we can get the relationship between all of these sides, of course. So let's go ahead and get this relationship. Let's move up. This relationship will then be the hypotenuse c squared t squared equals v squared t squared plus x squared. That's just the Pythagoras theorem from this triangle. All right. What I'm trying to do here by constructing this triangle is that I'm trying to find a relationship between t naught and t. The relationship that explains why this observer is observing that the tick is taking a longer time when he looks at the clock inside of the car that's traveling with the velocity v. So let's try and find this relationship. First we need t on one side of this equation, of course. So let's move this term to this side of the equation, and we'll get c squared t squared minus v squared t squared equals x squared. Then we can factor out t. And then we can divide by this term. And then we can take the root from both sides. So we take the root, we'll get t equals x divided by c squared minus v squared, and the root of that. But remember that x, we have x in this expression as well. So x is t naught times c. So let's replace this x with t naught times c. And we will then get t equals t naught c divided by c squared minus v squared, and the root of that. And we can divide both sides with t naught. So this will give us t divided by t naught equals c divided by c squared minus v squared. Can we simplify this a bit further? Yeah, let's square both sides again. T squared divided by t naught squared equals c squared divided by c squared minus v squared. Let's divide both numerator and denominator with c squared, and this will give us 1 over 1 minus v squared over c squared, and the root of that. This factor is called the Lorentz Vector, or short gamma. That's the gamma factor. So what we found now is that we found the relationship between t and t naught, called the Lorentz Vector or the gamma factor, which explains how the relationship between the time of the clock that's standing still and the clock that's moving varies with respect to the velocity of the moving clock. And all of this with regard to the point of view of the observer standing at the side of the road. That's the Lorentz Vector. But how can we reach E equals mc squared through this factor? Well, we need to find some kind of expression for the relativistic energy in order to reach E equals mc squared. And actually what we can do also, just to demonstrate what happens for different velocities, let us just see, to get a feeling for this expression. Let's see what happens if v equals 0. So if v equals 0, then this expression will be 0. We will end up with a 1 in the denominator, and the root of that is 1. So all of the gamma will be 1, equal to 1. And this will mean that t equals t naught. And this is exactly what we would expect if v is 0, because then the car would be standing still and the observer at the side of the road won't notice any difference in the ticks between the clock that's standing beside him and the clock inside of the car, right? But what happens if v is greater than 0? Well, if v is greater than 0, then all of gamma will be, of course, greater than 1, which means that t will always be greater than t0. And that's also what we observe in this thought experiment, that this person would actually see that the tick is much slower in the moving car. So t will be greater than t0. But let's increase v even more. What would happen if v limits the speed of light? That would mean, when we look at this expression, that this will come close to 1, closer and closer to 1, and the root of this will be a large number, an extremely large number, when v limits c, and the gamma will limit infinity when v limits c. So this would mean that t would also limit infinity. And what does this mean? Well, it means that from this point of view at the side of the road, if the car is moving close to the speed of light, this photon would, or this beam of light would, for this observer outside of the car, look like as if it's just standing there, if it's standing still, or going extremely slowly, as if the time was frozen or standing still inside of the car. So that's what this means. All right. So, by the way, this phenomenon is called time dilation. Time dilation. And that's basically the difference in the elapsed time measured by the two clocks. And the magnitude of this difference we get from the Lorentz Vector gamma. Okay. Now, in order to get an expression for the relativistic energy of the object, to reach E equals mc squared, to be able to derive that expression, then we need some help from classical mechanics. Classical mechanics tells us that if we exert a force on an object, force F, from the position x initial to the position x final, this being delta x or the displacement, this object will gain some kinetic energy, which would be equal to the work performed, which in turn is equal to F times delta x. So far so good. And in the integral form, with these limits, we can write xi xf f dx, right? But according to Newton's second law, F is the time derivative of the momentum. So F equals dp by dt. And we can also get a sense for that this is true because F equals ma, of course, the mass times the acceleration. And the acceleration, well, that's just the difference in velocity over the difference in time, right? And then we see that the momentum here, the mass, which is the mass times the velocity, varies. So we will get delta p over delta t. Hence the expression dp by dt for the force. Now if we consider being in the rest frame of the moving object, we will get the following expression for the momentum. P equals m dx over dt naught. All right, so how can we expand this? Well, we can use the chain rule to expand this expression even further, because the chain rule tells us that dx by dt naught equals dx by dt times dt by dt naught. That's what the chain rule tells us. But as we've already stated before, we already have a relation between t and t naught, right? And that relation is t equals gamma t naught. So if we differentiate both sides with respect to t naught, we would get just gamma. So this expression, that's just gamma, the Lorentz vector. So what is this expression then? If we look at this expression, well, this expression, the displacement by the difference in time, that's just the velocity, right? That's just the velocity. So dx by dt naught, that's just the velocity times the Lorentz vector times gamma. So we can finally write the relativistic momentum equals m times v times gamma. Great. So far, so good. So let's move on. So let's get back to our integral. We have the kinetic energy here, and we have the limits x initial, x final, dp over dt dx. So now we have an expression for the relativistic momentum here, but now we need the time derivative of this expression. So we need dp over dt in order to solve this integral. Well, dp by dt equals ddt gamma mv, right? This in turn equals d by dt mv times the Lorentz vector, which is 1 divided by 1 minus v squared over c squared, and the root of that. M, that's the matter, resting matter. Rest matter we can actually, because it's a constant, we can take out of the differential. So we would reach md by dt v over 1 minus v squared over c squared and the root of that. And how are we going to differentiate this with respect to t? Well, we would actually need to use the product rule. So let's rewrite this again. This equals md dt v times 1 minus v squared over c squared to the power of minus a half. So how can we utilize the product rule here? Well, what the product rule is telling us that if you have one function, this is a function, multiplied by another function, we can consider this as the other function, this expression, and this expression as one function, then the differential of that would be the differential of v times this function plus the differential of this function times v. All right. So let's go ahead and write this. So the differential with respect to time of v, well, that's just going to be dv by dt. Don't forget the m. dv by dt times, which the product rule says, times this function, right? So we just write times 1 minus v squared over c squared to the power of minus a half, plus, don't forget the m again, m, plus this function multiplied with the derivative of this function. Well, what is the derivative of this function? Well, as you can see, we have one function here, the brackets and the power of minus a half, and we have another function within this function, which is 1 minus v squared over, so we can actually use the chain rule to differentiate this with regard to t. So let's go ahead and create some space to differentiate this with regard to t by the chain rule. So let's just move this there. So d by dt of this expression, v squared over c squared to the power of minus a half, well, then we need to use the chain rule, and that will of course be, chain rule tells us that if we have one function within another function, then the derivative of that function will be the derivative of the outer function multiplied by the derivative of the inner function, right? So we need to take the power and move it down. That's the outer function. And then we need to take away minus 1 from that power. This times the inner function, and the inner function is this function. The 1 will disappear, and then we would just need to move down 2, so we will have minus 2v over c2, and that of course multiplied by, well, we'll have the chain rule again, so we need to multiply it by dv dt, because remember, we are differentiating with respect to dt, not dv, dt. Okay, so now we have this expression, which we can make even simpler. Of course, we can make it a bit simpler. Minus a half times minus 2, well, that's just gonna be 1, right? Yeah, that's just gonna be 1. So what we'll get is that we'll get v over c squared times 1 minus v squared over c squared to the power of minus 3 halves times dv dt. So we'll have this expression, and that is the derivative of, remember, the time derivative of this function, which we needed for the product rule. So what we're going to do now is just that we're going to move this function down here, included within the brackets here. So mv times v over c squared, 1 minus v squared over c squared to the power of minus 3 halves dv dt. We can simplify this further. Actually, let's do it on another page. I'm sorry for the mess being made here, but I'm running out of paper. All right. So let's continue with this expression and how to simplify it even further. Now we would have to write, of course, m dv dt 1 minus v squared over c squared to the power of minus a half plus, multiply the v with the v. So we will, and then we can also, to make it a bit tidier, move this term over here. M dv by dt v squared over c squared times 1 minus v squared over c squared to the power minus 3/2. All right, that's just great. Now, as you can see, we have two similar terms here. So let's try and factor these terms out to make something, to make this expression a bit easier. So let's factor these one out. And that equals to, let's turn this into a fraction as well. So I think it's going to be easier. 1 divided by 1 minus v squared over c squared, and that would be to the power of 1/2 plus, let's turn this into a fraction as well. So this would then end up being v squared over c squared divided by 1 minus v squared over c squared to the power of minus 3/2. Did that help? Yeah, well, what we need to do now is that we need to make the denominator the same for both fractions in order to unite the fractions. So let's go ahead and do that. How can we do that? Well, we can do that, no minus there, we can do that by multiplying the numerator and denominator in this fraction with this term, right? So let's go ahead and do that. Then we will end up with 1 minus v squared over c squared divided by 1 minus v squared over c squared, v squared over c squared to the power of, we need to add 1 because we multiplied both numerator and denominator with this expression. So we get 3/2. That's great because that's the same power as in the other fraction. That's great. Plus v squared over c squared divided by 1 minus v squared over c squared to the power of 3/2. Well, look at this. This is just great. We can unite these two fractions and this will cancel out. So what we will end up with is 1 over 1 minus v squared over c squared to the power of 3/2. And this is very similar to the Lorentz vector, right? It's just that everything here is cubed. So this is basically just the Lorentz vector cubed. That's the Lorentz vector cubed, right? And of course, do not forget this term. All right, that's just wonderful. So let us take some deep breaths. That was quite a challenge. And let's move on. So now we can write an expression for our relativistic kinetic energy by writing relativistic kinetic energy is the limits initial to final position. And then we have gamma cubed m dv by dt dx. And what we can do now is that we can actually, we can take out the m out of the integral because it will be a constant. And then let's just see, let's just write out the Lorentz vector as well to see if we can integrate this somehow. M x initial, x final, and then we have the Lorentz vector, and that will of course be, let's see, did we forget something? We have m, no, we didn't. Wait, let me just check if we did. No, we didn't. We're all good. Yeah. most important thing in order to be able to integrate this is you see a pretty severe problem here. We can't integrate with respect to x because we don't have the x variable in this expression at all. So what are we gonna do? Well, we need to think about it. We need to do something with this expression, right? Let's take this expression, dv over dt, and let's use the chain rule again. Just like before, let's use the chain rule again. The chain rule will tell us that dv by dx times dx by dt. Yeah, that would be the same as this one through the chain rule. That's completely right. And then we have dx here. So what can we do with this one? Well, they cancel out right there, right? So what we'll end up with is dx dt dv. So now we can use this one. Now we would integrate with respect to v. That's just great. So new expression for relativistic kinetic energy is x initial, x final, gamma cubed m, or actually we can write the m here, gamma cubed dx over, this is just the, guys, this is just the velocity, right? Displacement in the displacement over the time difference. That's just the velocity. So this expression will be v dv. That's just great. So we will get v dv. That's just fantastic. But if we integrate with respect to v, then we also need to change the limits. So we can change the limits from rest to some velocity v here. Okay, we change the limits from that to some velocity v there. All right, so what did we end up with? Well, we will end up with m0v. Let's write out the Lorentz factor here. Let's just write it out, see what happens. So Lorentz factor, then we need to have the v still there, v divided by 1 minus v squared over c squared, and that to the power of 3/2, right? Because it's cubed, so to the power of 3/2 dv. All right, how do we integrate this expression? Well, that's going to be a challenge. Let's continue on another page. All right, so as we've already said, kinetic energy equals m limit 0 v. Let's try and rewrite this, see if something like that would happen. Let's try to write the Lorentz factor cube by itself, just to see if we can get a better overview. Minus v squared over c squared to the power of 3/2 times v dv. How do we integrate that? Actually, I think we should use the substitution rule now. Yeah, let's use the substitution rule because this expression is a bit more complicated. So let's use the substitution rule for that expression. So let the expression 1 minus v squared over c squared be u. Let that be u. So what are we going to get? Well, we are going to get, what we want to do now is if we let this be u, then we want to integrate with respect to u as well. We want to integrate with respect to u as well. So du over dv, we need to somehow get an expression of v dv of this. We need to somehow get an expression of this through substitution, because we want to integrate with respect to u. because we substituted this term with u. All right, so what is du by dv? Well, that is going to be, the one is going away, so we will have minus 2v over c2, right? And this will give us, this will actually give us, we can break out v dv from this expression. This would actually give us, if we do some cross multiplication here, this will give us c squared du equals minus 2v dv. We have v dv here. That's just great. That's what we want. So v dv equals c squared du divided by 2. That's just amazing. So let's go ahead and replace v dv with this expression. Let's go ahead and replace it with that expression, and let's replace this expression with u. So what we will end up with is from 0 to v, and then we will get 1 over, u to the power of 3/2, to the power of 3/2, and that multiplied by minus c squared divided by 2 du. So we will have this expression. All right, and don't forget the m. M is still around, m is still there. So what we get now is that we can actually try and simplify this a bit. What we can do now is do like this. It will of course be 0 to v m minus c squared divided by 2 u to the power of 3/2 du c, that's a constant. That doesn't have to be in the integral. We can take it out. MC, look at that. We're getting close. We are getting closer and closer to the... oh, actually, we can take out the 2 as well. It doesn't have to be there. So it will be mc squared divided by 2 minus mc squared divided by 2. And that will be 1 over u 3/3, and that will be minus mc squared divided by 2, 0 u minus 3/2 and du. Yeah, this actually looks something that we can integrate quite easily. We can integrate that quite easily, that expression. So let's try and integrate that expression. I don't think that will be any problem at all, actually. So the primitive function of that would of course be u. We need to add 1 to the power, u minus 1/2 divided by minus another 1/2 plus c. We don't need the c because the limits will cancel out the c's. And don't forget the minus mc squared divided by 2 factor. So all of this times mc squared divided by 2, which will then give us, it would give us minus mc squared divided by 2 upper limit. If this is v, wait, oh yeah, we need to write out it. We need to write the we need to substitute it back in. Oh yeah, we need to substitute it back in. But we can make this simpler, of course. Let's do that. mc squared divided by 2 to the power, and that's going to be minus, minus 2, right? Minus 2 divided by the, and then we can, yeah, that's just going to be u, the root of u, the root of u, v0. All right, so that's a sim, but we need to replace, we need to put it back. We need to put this u, this term, we need to put this term back in, because now the substitution has already fulfilled its purpose. So we need to put that term back in. And what we'll get is that we will, of course, get -2, and then we put that term back in, which is 1, the u term is equal to 1 minus v squared over c squared, and the root of that, yeah, that's the Lorentz function, right? We have a Lorentz function here, quite close. Not yet, but pretty close, from the limit 0 to v. Let's see what happens when we insert the limits. And then this will give us, well, if we have v, then we will, of course, get this expression and nothing else. But wait, before we do that, we can take out the 2 as well. We don't need the 2. We can take out -2 here. And -2 times -1/2, that would cancel out, right? Yeah, so we will just get mc squared there. That's great. We will just get mc squared 1 over 1 minus v squared over c squared. And now we get the Lorentz function, the Lorentz vector. Now we have the Lorentz vector. I thought that, yeah, because it looked so similar, but now we have it. Of course, we could have taken out this 2 before. Good that we saw that. All right, so now we have mc squared, and we are still within brackets. So this would then be, of course, the upper limit, and the lower limit would be when v is 0. When v is 0 here, this will be 0. The denominator will be 1. The root of 1 is 1. 1 divided by 1 is 1. So it will be 1. It will be 1. It will be 1. That is very, very interesting. So what we get is that we get this equals mc squared times 1 over 1 minus v squared over c squared, and the root of that, -1. And this is the Lorentz vector, which equals mc squared, well, let's write gamma -1. Oh, amazing. Amazing. Now we have a really nice expression here for the relativistic kinetic energy. Let's actually see what that means for the relativistic kinetic energy. Let's see what that means. Relativistic. If v, in this case, if v equals 0, that means if the object is not moving, then this will equal 1. The Lorentz vector will be 1. 1 minus 1 is 0. So then the kinetic energy, the relativistic kinetic energy, will be 0 as well. And that's exactly what we would expect. So it seems to be correct, this expression. And yeah, it's pretty interesting. Let's try and discover what else this expression has to offer, because now we're getting really close, I think. All right, so this expression tells us that the relativistic kinetic energy equals mc squared gamma minus 1. All right, so and this is gamma mc squared minus mc squared. So let's try and rearrange this. If we have the kinetic energy plus this factor here, plus mc squared. So we have the kinetic energy plus this factor will equal gamma mc. So this kinetic energy plus something equals, this must mean that this is a total energy. So this is E total. total energy, the total relativistic energy of an object is gamma mc squared. Yeah, that's pretty cool. Gamma mc squared. Yeah. Yeah, so should we try and see what else this gamma function has to offer us, because we would like to relate that somehow to what we can experience. So if we write the gamma function 1 minus v squared over c squared to the power of minus a half, if we write it this way, and things that we can experience, v is always going to be lower than c, always lower, which means that this expression is a binomial with a power. Okay, so we can use the binomial theorem. Binomial in order to expand this expression. Binomial theorem. And this theorem tells us that if we have a binomial 1 plus x to the power of n, then we can expand this by using the following algorithm. It's going to be 1 plus nx plus n times n minus 1, x squared divided by 2 factorial plus n times n minus 1 times n minus 2, x cubed divided by 3 factorial, and so on. Let's just start off with the first three terms here, see what we're going to get if we expand the Lorentz vector here. Lorentz vector. So in this case, the x, it will be minus v squared over c squared, right? Yeah. And then the n for the Lorentz function will be minus a half. So let's use this algorithm then to try and expand the Lorentz vector. So what we will get, if we start off slowly, we would get something like this. We will get 1 plus, let's see now, 1 plus minus a half times minus v squared divided, divided by c squared, plus minus a half again times minus a half minus 1 minus v squared over c squared, and the square of that. Yeah, this is getting tedious. Minus half minus a half. Yeah, let's write it out and soon we'll be done. Bear with me. Minus 2 minus v cubed, v squared over c squared cubed, and that divided by 3 factorial, that divided by 2 factorial, which, if we simplify it, would give us 1 plus, that would be, that would be v squared over 2c squared, and that in turn would be 3/4, that would be 3/4 times v to the power 4 divided by c to the power 4. 2 factorial is 2 plus, and that would be minus, that would be minus 3 halves, that would be minus 5 halves, minus 15 eighths, minus, it's going to be v to the power of 6, c to the power of 6, divided by 3 factorial is 6, equals 1 plus v squared over 2c squared plus 3 eighths, v to the power 4, c to the power 4 plus 15 48 times v6 over c6. It's going to be that. But what are we interested in? Well, what are we interested? What we are experiencing, we are only experiencing v's that are much, much, much lower than c. So you can see here that if we multiply this by mc squared, all of this expression, we can see, okay, we will get the 1, so that's a keeper. This one too, yeah, it's a keeper too. It's a keeper because those two will cancel. For this one, we will still have a c to the power of 4. We will see they will cancel out just to the c to the c squared, so it will still be quite a high number. So actually we can disregard this term and this term, because they will be very, very small when v is much, much lower than c. So for the experience of our own senses, what we can experience, we can only actually include these two factors. Yeah, because these other factors will be very, very small. So the conclusion is that we can ignore all terms with a higher order than v squared over c squared. Yeah. So let's see what we'll get then if we ignore this term and only keep these two terms as the so-called gamma. Yeah, it's not a true gamma, but this is what we'll keep out of the gamma. So this will give us the expression mc squared for the E total, for the total relativistic energy, mc squared times 1 plus v squared over 2c squared. That equals mc squared plus mc squared v squared over 2c squared. Those will cancel out, equals mc squared plus mv. Oh wow, so you all recognize this term, right? This is the kinetic energy in classical physics. So in classical mechanics, this is the kinetic energy of an object with the mass m and the velocity v. That's very interesting. So for things that we can experience, Newton was right for v's that are much, much smaller than c's for what our senses can experience. Then this expression is completely correct. But you can also see here that this term, it's completely independent of v. It doesn't have a v variable within it. So even though the object is actually still, even when v is 0, the object will still have this term. It will still have this amount of energy. That's interesting. That can be considered as the resting energy of the object, or you can think of it as the energy that is required to create this mass of the object. And that energy can be released. It's a great amount of energy. Imagine it's m mass times c squared. So you can have a pretty small amount of mass and still get lots of energy because of this c squared factor. And that's what we observe, for instance, when matter and antimatter collide. Then this energy is released, huge amounts of energy. And that also happens in the nuclear fusion in stars. Fusion, hopefully we'll reach fusion on Earth that has a net power supply that's positive, so that we can secure our energy supply. All right, I think that was it. I hope that this video has increased your knowledge about how we can get E equals mc squared, or more correctly, E equals gamma mc squared, and a feeling for what it means, a feeling for the Lorentz vector or gamma, and yeah, see you in the next video.